Hello and welcome to chapter 6, which is networking layers. This will be one of the many mini lecture that we do in this course. So without further ado, let's go ahead and start talking about chapter 6. All right, what quickly we'll cover in chapter 6 will explain how network layer protocols and services support communication across data network. More importantly, we'll describe the purpose of network layers in data communication, why we need it, what does it do. Explain why IPv4 protocol requires other layer to provide reliability, because IPv4, as you know, it's what we call connectionless, not reliable, right? We will also try to explain the role of the major header field. I'll just give you an idea about dissect an IPv4 what do you call header and looking inside of it. And finally, all the way down, and not finally, there is more. In 6.2, we're going to explain how routers enable end-to-end connectivity, what software, how does it do it, how does it make decision, and how does it know how to forward packet from point A to point B. Explain how network devices use a routing table to direct packet from point A to point B. Routing table, as you can see, host computers, Linux, Unix, Windows, they all have their own routing table, and they use their routing table a lot of times to find their default gateway, which is where to forward their packets. Compare a host routing table to a real routing table at any given Cisco routers. Finally, this is some of the hands-on and show and the demo that I'm going to show you. Explain how devices route traffic in a small network. Describe the common component and interfaces of a router. This is the physical components. Describe the boot up process of a Cisco router, and in this case, you're gonna find it is similar to any computer booting up process, either Linux or Windows or Mac. Configure, and finally, we'll do a little demo configuring a Cisco router. So we'll spend some time on configuring a router, basic configuration, for instance, how we enable, how we got config T, how we change the host name, how we break an interface up, how we assign an IP address, and so forth. Configure two devices interface on the Cisco routers. I'll show you that. And configure devices using the default gateway. Why certain devices, such as switches and client, may need the IP address of a default gateway. And before I go even further, I just want to remind you that a default gateway is nothing but the IP address of a given router. All right, so first of all, the networking layer, if you see it, it's layer number 3 on the OSI model. It is layer number 3 in the OSI model, and it plays very important roles. So some of those roles, if you want, one of the is addressing of end devices. You may have computers here. This computer A need to send data to computer A to this host right here. Another way, host 192.168.32.11 has some packet to send to 192.168.36.5. It is his request will be sent down till it reaches the network. It is at the network layer that decision is made where and how to get to this device right here. So it is. Additionally, it's also in charge of the encapsulation and de-encapsulation process. It takes whatever the transport layer sends down and encapsulate it. This is at the source, and then at the destination, it does the reverse. Finally, like I said quickly, at this layer also the routing process happen at this layers, and the encapsulation also happen at this layers. Looking again, a little bit more information, looking at the network layer, the two most common protocol that work at this layer, we do have other protocol, but the most common used one is IPv4 and IPv6. IPv4 and IPv6. And IPv4 and IPv6 are not one protocol or two protocols, they're set of protocol. Another way, there are hundreds of what it calls of protocol. All right. In the next slide, what you're looking at is an IPv4 packet header. Another way, if you somehow, when one PC sent another PC a request for whatever connection or for services, and you capture that data, using Wireshark, which is the most common used tools, and you dissect and you look inside of it, there is a wealth of information in that packet header, a lot of information. And this will really help you understand how does a router make decisions. So there's a lot of information over here that router needed to make a decision, and quickly I gave you some information. For instance here, the first piece of information you may find in any given header, it's what we call the version, and it defines what version of IP is it running. Is it using IPv4 or is it using IPv6? The length of the header, the differential services known as service DS, and this is used by router to define or to calculate the priorities, how fast or how quick or how slow this frame or this packet need to be sent. And this is the data itself. This is what need to be sent. This is the data itself. Every single packet will have an identification. Every single packet will have a flag. Every single packet have what we call fragmentations offset. Every single packet has a time to live. A time to live, it's every single packet has a frame. It cannot stay forever running. For instance, if PCA sends a packet to PCB, for instance, and packet never made it to destination for whatever reason, that packet cannot stay on the line forever. After a given time, it will self-destruct. It will just other machines will just disregard it. Nobody will pay attention to it. Nobody will process it anymore. Header checksum is commonly used to calculate errors. And for you, the most important thing is all the way down here. Inside of packet, you'll find the source address, mean the machine that is sending this packet, and down here you see the destination. Again, this is not every single thing in a packet header. This is just some of the important information that we may find. And by the way, looking at this from security perspective and from hacking perspective, there is a wealth of information that I'm looking at right now. All right, IPv4. If, for instance, going back here, if the version of IP database used here is IPv4, they want you to know that IPv4 it has a lot of limitation. By the way, let me tell you that every single computer in a network, requires an IP address to communicate with other. I know that exception where a machine may not need, but in general, at this level for you, almost every single station you'll ever touch will require an IP address. An IP address is used by a machine to logically identify itself. The closest thing I can compare it to, I compare IP addresses, IPv4 and IPv6 in this case, to if you want, to a phone number. Without a phone number, your phone will not work. Your phone will become obsolete. It is exactly the same thing for a computer or nodes, not just computer. Every node that need to talk in a network have to have a unique IPv4. IPv4 is logical, all right? It's logical. It's changed every now and then. If you have a computer, if you take your computer to your college and you plug it in a network, you're gonna have one IP address. You take it home, you're gonna get a different IP address, and if you take it work, you completely get different IP address. So IP address does change. IP address is 32-bit. If you remember from the header, if you count all those bits as 32, it's 2 to the power of 32. So how many IP address IPv4 will give us? If you take 2 to the power of 32, will give us about 4 billion possible IP addresses. Every single no two computers in a given network or segment can have the same network, can have the same IP address, need to be unique, and this is the case of the internet. No two computers on the entire internet can have the same IP addresses. IP addresses need to be different. Now, one of the problems that we never engineered, nobody or scientists ever thought it would be possible, that as of today, not after that, as of years ago, we run out of IP addresses. For computers on the internet that requires unique IP addresses, we run out of IP addresses and we don't have IP addresses to give them anymore. So as a result, we have come out, scientists and researchers have come out with dozens of possible solutions to mitigate the depletion of IPv4. Some of those solutions is something known as NAT, which stands for Network Address Translation. What NAT does, for instance, for your home or your computer or your home or for your business or your work, instead of giving every single computer in your network a valid IP address, a valid IP address on the internet, another way we call it public IP address on the internet, what NAT does, takes every single computer network and give it one single IP address. It shares it with every single device on your network. I am 100% that at your home, if you go and type ipconfig/all and you get 192.168.something, that is definitely your NAT. Your modem, your gateway, your wireless access point is using NAT. Sometimes they use NAT, sometimes we use something similar known as PAT. If you truly want to know your real IP addresses, go to Google and type what is my IP address. And you're going to notice that only IP address you have, it is really shared using NAT with every single device at home or at work. To solve the depletions of IPv4, scientists and researchers have introduced something known as IPv6. Unlike IPv4 is 2 to the power of 32, IPv6 is 2 to the power of 128, right? And it's really some research has said it's enough IP address, is enough numbers to give to every single atom on Earth in another Earth. So it's in decillions. The numbers are in decillions, right? If you look down here is the number of what you call it. I think there are 340 in decillion possible IP addresses in what you call it. So IPv6 came in to solve the problem because NAT itself, although is a good solution, it does create some problems itself, especially when we're talking about IPv6. So we're talking about IPsec. All right, let's take a quick look at IPv6. As you can see, IPv6, unlike IPv4, is much smaller and much simpler if you want. So if you remember IPv4, we have a lot more. For instance, we have TTL. It is not here. We have what do you call it? A differential. It's not here. So you could look, if you compare IPv6 packet to IPv4, you will quickly learn that IPv6 is much simpler. It's much simpler and much smaller. Now, moving to routing. Very important question, valid question, how router makes decision. Let me give you this, for instance. Let's pretend this is a small network, all right, that has had PC1 and PC2, and PC1 or PC2 need to go outside, need to access resources located at this host here, which is over the internet. How does he do that? Well, the first thing that a PC does, PC can request, a host can send packet to itself. Host can send packet to, for instance, if I go ahead and type ping 127.0.0.1, this packet, it's not going anywhere, this packet and staying within. But if I can also send it to this computer, I can ping the IP address of this local host, or I can ping the IP address of this router, the default gateway, or I can ping this machine right here. So a machine can talk to itself, can talk to another machines in what we call a network, or can talk to a remote computer. The question number one is really interesting: is how does a computer come to a conclusion that the machine he needs to talk to is it itself? Is it another machine in a network, or is it remote? It does that by using a process known as ending, the ending process, which is a process we're going to talk about it in the future. All right. Now, using the ending process, if a computer comes to a conclusion that the machine he needs to talk to, it's not local, it's remote. So what it does, it sends that request to its default gateway. And what is a default gateway? A default gateway is an IP address of the router. So after the ending process, this computer comes to a conclusion that the server needs to talk to, it's not local, it's remote, and the only way to reach it is by sending that request to its default gateway to the router, and the router takes that request and sends it outside. All right. Now, question: how did the PC make that decisions? How did he know this router? A PC itself look at its own router, its own routing table. Every computer, be it a PC or a Unix or a Linux, uses its own routing to figure out what it needs to do when it has a packet to send it somewhere else. That's what the routing table, think of it as a map, think of it as instruction that devices use to find out what they need to do with certain packets. Should I send it to computer inside? Should I send it to my router, or should I just disregard it? Disregard it. So you can see it right here. If you go to your Windows machine and type netstat-r, you should be able to see the routing. And you can see right here that this computer right here, he knows the IP address of the router right here. You can see it right here. So he said, any packet with any IP, when you receive any IP with any subnet mask that you don't know what to do with it, send it to 192.168.1. This is your gateway, and this knows what to do with it. So this is what this routing table, the first line in the routing table is. You can also type route print, and it prints the routing tables for you too. All right. All right, router packet. Now so let's pretend now the PC did find the router they need to forward the packet to. How does a router, now the question now, how does the router itself forward this packet from point A to point B? In other words, how does it know? How does it know? Well, it knows by listening, knows by communicating with neighbor routers. When routers are physically connected to each other, they exchange their routing table. Every single router shares its routing table. I'll give you a good example. For instance, this router advertises, hello, my next neighbor router. I just want to let you know that I can access 192.168.10 network.0, and I can also access 192.168.11.0 network. And this router said, hey, I would like to let you know that me too, I can physically access this router, the router 10.1.1.0 and 10.1.1.2 in addition to this. So you could see that they are physically connected to each other. They're physically connected to each other. So I'm going to stop on part one, and I'll start part two in a second. And